In the face of an unpredictable future, we are all called upon each and every day to think of out-of-the-box ways to tackle challenges to our environment, well-being, or where to get raw materials for your chocolate and spaghetti enterprise. Welcome to the Grand Challenges Podcast, a show about inspiring individuals who are stepping up to these challenges and are here to share stories about their own personal journey towards making our world a better place. I'm your host, Peter Marcus Bach, a modeler obsessed with controlling and automating things with a passion for connecting across expertise and providing you access to knowledge from the cutting edges of science, engineering, technology, and design. My guest today is Professor Peter Vanrolleghem, a bio and wastewater engineer from Université Laval in Quebec City, Canada. Peter is widely known in the urban water and modeling fields and has a lifelong passion for understanding how we can engineer and control the microscopic world for the benefit of environment and society. Today's wide-ranging show takes us from chocolate and spaghetti deep into the world of urban wastewater, where major shifts towards resource recovery and digitalization are taking place. We also delve into Peter's journey and his life-changing encounters with serendipity and mentorship in his career to date. Detailed information is provided in the show notes over at petermbach.com/podcast. Thank you for joining, and please enjoy the show. Welcome to the show, Peter.
Thank you for having me.
It's a really exciting moment for me to have you here because I've known you for a very long time and you've been a long time mentor to me as well. So looking forward to having you share a lot of your experiences and to learn something every single day, like I learn every single day.
Happy to share, yeah. It's good.
Yeah. I guess one thing that I noticed when I was reading your bio and learning a bit more about the time before I knew you was this nickname that you were given, which was called Respiro Peter. Which was actually kind of strange because that Respiro to me sounds like something related to breathing. And I thought, well, Respiro Peter. You want to tell me a bit about that?
Oh, yeah. It is basically the start of my scientific career, I think. I was doing respirometry, which is the technique by which you see or you evaluate how organisms consume oxygen to degrade pollution. So it's basically giving you a direct view on how organisms do the work we want them to do, live and grow. And respirometry, I did so much of it that respirometer became respiropter. Respiropeter.
Respiropter.
That's how it came about.
Okay, interesting. And so you've been very interested in biological processes. And I remember in one of our chats, you once told me that you may have almost gone into nuclear engineering. What was the whole story around that?
I think I like just challenging issues or problems. So I was very much intrigued when I was a kid about space and astronomy, but also on the very small. The universe is very big, and then the very small is the nuclear part, and they come together in this, where you look at how suns work and how that all gets together. So the nuclear power thing was pretty popular in Belgium. So you had 60% of our energy came from nuclear power. And it's a problematic situation because you have nuclear waste. But you have got lots of benefits. So that intrigued me to how it worked. And then the microscopic thing, go beyond what you can see and still believe that it's going to work like this was intriguing. Unfortunately, in secondary school, I indicated I would like to do this. They said, well, this is an entry exam you have to do to get there. It's like the toughest engineering you can do. And I basically never made the engineering exam. I never tried. I just studied for it and I said, no, it's not going to be my thing. So I went into the biotechnology, which is also small and complex. It's complex in a different way. It's not complex because it's too small, you can't look at it, but it's small and complex. So you have enzymes and all these reactions that are happening in a cell that are really interesting to understand and see how biology has made that and evolution has made that this can all work together for organisms to grow and prosper.
So in a way, it was your fascination with the microscopic aspects and the complexity of the biological world. And I guess you were intrigued by being able to tinker with it. And so you weren't going to just settle for basic understanding. You wanted to go further in that.
Microorganisms was intriguing, but then everything that had to do with biotechnology, molecular biotechnology, how man could change organisms to do things for them. How to use organisms, that came later, how to use organisms to do pollutant removal. All that came together in my choice to go for biotechnology, which in the 80s, which is the time I was in secondary school, became a very hot topic in Belgium. Because we had Plant Genetic Systems, which is a company that was transforming tobacco plants and producing specialty products. And they had a patent. It was like, they were like going for the Nobel Prize. Like whole Belgium was thinking these guys go for the Nobel Prize. And it was very exciting because it was really going for the understanding of biology and its complexity, but then being able to manipulate it in such a way that it did good things for society. So that was really exciting. And so I went for this biotechnology choice then after my secondary school. And that was then developing quite well. I became an industrial microbiologist, so bioengineering, industrial microbiology, in the food technology aspects, in the environmental, there's different applications, so environment, food, fermentation products, so organisms that produce antibiotics and insulin and what have you. And then first in my career, I started really doing biotechnology in the pure sense of pure culture. You have an organism, you change it, and you produce something that is high value, like in the pharmaceutical industry. But that went wrong because my professor got mentally sick, so I had to bail out suddenly, and then I had to go to, find another job, right, another topic. So I went and got the chance to meet Willy Verstraat, who was a professor of mine, and we may talk about our mentorships that were so important in my life, but he was one of a kind and allowed me to go and look at microbes, how they do work in the environmental systems. So looking at wastewater treatment, so that became then the topic of my PhD.
And so you did your PhD in Ghent in Belgium. And this was back in the 90s.
Yeah, early 90s.
And it was in the topic of, as far as I can remember, it was in bioengineering and then environmental technology that you went on to do. Yeah. So bioengineering is really all about how we can control microbiology to help us create a kind of product, whereas then environmental technology is then more in the developing of the technology that uses these biological processes.
Yeah, but if I would say that we do also bioengineer, I will always claim that I'm a bioengineer because you use your knowledge about biology to engineer systems around them that allow you to benefit from the goodies that they do without knowing it. They do it for themselves because they want to grow. By doing that, you let them do pollution removal. But they like to do it for us because they grow, so they get more of them. And that's the whole idea of life, I think, that you want to be more and be successful in evolution. So bioengineering for me is what we, by knowing how the systems work, by our models, I'm a modeler, so by our models we can organize this biological system in such a way that you get the benefits or maximize the benefits with the minimum resource you have to put in.
So using the models to help, in a way, achieve that kind of optimization, that kind of control.
And the technology as well. So the technology is there then is the tools that we have to engineer. So we need to have reactors and pumps, but this is then something different. I think I'm not a specialist in that. I think I'm specialized in knowing what to do to make organisms do what we want them to do.
And you've worked within, in a way, the food industry, the agriculture industry, and now you're in wastewater.
Yeah, this was a special situation. So when I did my PhD, my professor then saw in me something that he said we need this at the faculty. And we had a department of mathematics and process control and statistics. But the professors, they were all mathematicians or like pure scientists, had no connection to the bioprocesses. And so my professor, who was a big person in the faculty, he said, this must be changing. We must have a person that knows bioprocesses to do this teaching in mathematics and modeling and control. So he basically pushed for the faculty to open a position for me, and I was lucky to be there and got his support. So I made that. And the difficulty for me at that point was that I was the modeler. But the faculty came with all possible modeling questions to me. So it was, the faculty is a faculty of agriculture, food, chemistry, forestry, water resources.
Oh, wow.
So in theory, I was supporting every modeling and statistics person to come by, I would go in. And I did that because I'm very interested in many different things. So I'm a generalist, so I got every time excited when people came with a problem. And I could see that the methods that I had for modeling were applicable to all these systems. I did modeling of farms to find out which fraction of land you should not put manure on to have more flowers, to have more diversity. And I was doing spaghetti to find out how you could increase the water content of spaghetti, because then you have waste you can sell. So increase the water content of spaghetti such that you make more money as a spaghetti producer in Belgium. I worked on chocolate which becomes white if you let it stand, and it becomes like this white thing. How can we reduce that white thing on the top of chocolate? So it's all modeling these things, and it was really very stimulating to find out that these tools, these methods I had, I could apply them to everything. The problem was it is killing yourself, because every time somebody comes with a question to you, you have to understand what he's talking about. Why is chocolate getting white? Well, you study and study and study. So I was always studying new things, which was nice, but it was immensely time-consuming and difficult to keep track of that. And I lost then the link to what I really wanted to do, is to learn about modeling methods.
Interesting.
So I was investing a lot of time in understanding systems rather than developing my skills in terms of modeling.
Yeah, so it seems that even from the early days in your research career, you've already been thrown across the different disciplines because you had a more generalist skill, which is in the modeling.
Yes.
And it's fascinating to see how these modeling skills have a lot of similarities across these different fields that you've been looking at.
Indeed.
That there seems to be that common thread.
And very quickly, a very nice experience I had was... So I worked on this chocolate thing with a group of people in the faculty who were really good at chocolate, because chocolate is a Belgian thing, right? So they were really good. So they had a problem. They missed the modeling skills to move beyond what they were able to do qualitatively. So when I was working on this modeling of these phenomena, observations, very quickly I could see that the models that I've used for wastewater treatment could be applied directly on the chocolate problems that they had. And within 6 months, I was called in as a keynote at a food technology conference because I brought something that they hadn't known, that hadn't seen before. And that same thing happened to a postdoc of mine, Chris Heijnij, who is now a big shot in Denmark at DTU. He did the same with the pharmaceutical industry. He basically used the wastewater treatment modeling approaches and applied them to the pharmaceutical industry. And he has revolutionized the way they model in the pharmaceutical industry, which is nice that you realize that what you do in a certain discipline, if you're a bit open to looking at other things, you can just transfer and make a big difference.
Yeah, I find it quite amazing how with just some openness you can already achieve some basic cross-pollination of knowledge between two seemingly different disciplines, and how this can then feed into new revolutionary approaches.
I like that I was part of it, and I realize I can explain that to people. Because not many people are sufficiently open to see that what they could do, they could move into another discipline. And I've been suffering from it, because I moved into many disciplines, so I was suffering to always learn and have to learn too much. But that you can then make a difference, and a relatively easy difference, because what I did in the food technology area was just bringing the basic methods I brought in there, but they had not seen this. So it was like, whoa, what's this? And then other people built upon, because I stopped doing that. I could not follow. So when I moved out of Belgium, I stopped doing anything with chocolate and spaghetti and farms.
And I was going to actually get to this, because in a way you've now found your home in the wastewater field, but you had to make that step somehow. And I believe you still began with that at some point in Belgium, or did that happen when did you actually geographically force yourself out?
I did my PhD in wastewater, but then with this professorship I got, I was basically opening up to many different disciplines. And that was about 10 years I did that, and was basically learning about many different disciplines. But I got, that's another part, it's an important part of my life. So at some point for my process control development, my professor in that new department, the mathematics department I was in, said, you don't know enough about it, you should go and learn. He told me, you got 6 months, you go take a place and you're going to work and study, and you come back with process control background. And that led me to go to Montreal. Now that decision is has made a whirlwind in our lives, because Annick is my wife, Annick and I went to Montreal for 6 months to study process control. But we came back, and a month later we were homesick because we wanted to go back to Montreal, because life had been so incredibly different to what we had in Belgium. In terms of quality of life, it was so good. So since then, we were looking at moving out of Belgium. We basically wanted to leave Belgium, and not for professional reasons, but for life quality reasons. And so then we talked to people in Quebec City, because we had good friends there, and a professor in my university now, the Université Laval. So they were aware of this, and they worked on it because I had a good CV, so they knew they would be able to catch a good person. And they worked on it for many years, I think. And after, in 2003, they were able to get this chair position that was intended for me. So then we applied. That left me going out of that diversity of application areas of modeling to the wastewater area. They hired me for modeling water quality in general. So the whole water cycle from, I say now, the water quality in the dropping from the tap, from the cloud, and it flows down to the sewer system treatment plant into the river. So that's what I do. So it's much more restricted, but on purpose. I didn't want to go into drinking water. I didn't want to go into groundwater. I didn't want to go in chocolate anymore. I just wanted to be on the water side, because I knew that if I wanted to dig deeper, I had to select a domain of application.
You didn't want to go into chocolate anymore, just eat it.
Just
right?
eat it, yeah, exactly.
I mean, I guess if you do too much of the modeling or the development around it, you probably won't enjoy it in the end as a result.
Sure, exactly.
I guess one aspect around your time at Ghent, which in a way highlights, I guess, a big achievement of yours in Ghent, is the Biomath group. Mm-hmm. Can you tell me a bit about what Biomath sort of stands for? So
Biomath is this creation, I think, by Willy Verstraeten, so this professor that was my PhD supervisor. He saw this problem of they have a mathematics department, but they're not knowing biology. So he felt that this is not good for the education of the students that come out because they would not make a link between what mathematics can do and biological processes. So when I arrived there, I know how important it is to come up with a name. So we came up with the name biomass. So I was working together with people that were doing simulator work and doing fancy programming, I would say, and still do. And then we created this idea, okay, we are working on biological process. What's the term you use for this? Well, biomass came up, and that's how we created the name biomass. And it was this exact mix of good statistical and modeling methodology people, like fundamental people in that area, with then people that know the biology quite well, but have openness to and apply these methods. So that was a strength, and it's still the strength of that group, because if you look at in the world, what the biomass people come up, the students that come through that, they're all very good in this domain of modeling and application and quantitative thinking about processes.
Actually, it's funny when you think about it, but sometimes the simplest combination of disciplines make the best names, bio and math.
Yeah.
And now I guess you still have a lot of contact with that group.
Yeah.
If there's a lot of collaboration.
Recruiting people from there. So I still think that my best graduate students come through that training program. It's the people that have done a master thesis in biomass are like always very well equipped to work with me because they have like the basics that I need to do research and in this mix of the process and the mathematical skills you need to do it properly.
Now you're in Quebec at Université Laval in Quebec City.
Yep.
I remember looking at a map of Montreal and I noticed that there's a Laval in Montreal as well, which is 3 hours away from
where I live, yeah.
And you've got your group Modelo, which has been around and quite active in the field of wastewater engineering, but also, I guess, urban drainage in a broader sense as well.
Integrated urban wastewater systems, I would say.
Integrated urban wastewater systems. Yeah. I mean, I guess one of the things that connects us is a paper that I wrote on integrated modeling, and I think the terminology aspect has been a very interesting topic around the integrated modeling sphere. But we'll get into that shortly, because I think that's something that it's also quite dear to you. But you're in Quebec, you have your own group there now. I guess it's grown quite a lot since you started, hasn't it?
Well, the biggest transition, I would say, a few years where you have a few people, 2, 3, and then it builds up and then it explodes. So in biomass, I went from myself to 25 at the end. It was 25, which was too big. So I just had too much success in project writing. What I wrote, I got, and it was, in the end, getting too much. If I would have stayed for another few years, I would have gone to a burnout. I'm pretty sure I was just doing too much. So what the good thing in Quebec is that since I've reduced my scope, just doing wastewater, there's less projects that come my way. And the projects in Europe are big. If you go involved in European Union projects, they are really big and difficult, complex to make. So you spend a lot more time per project. And they're bigger budgets as well. So whereas in Quebec, the budget per project is a bit smaller. So that means that to grow a group of 15, which I have now, 15, 20 people, is a good size. I can manage it, and I've become more experienced in managing a group, so I can handle a group of 15, 20 people quite well. But that's big for Canadians, that's standards. So compared to Europe, the Canadian standards are smaller research groups per professor. And that's, different ways. You can go deeper with your students. I think I'm maybe not digging deep with my students. I prefer to go quick and fast and far away rather than digging deep and I'm not the person that is digging really, really deep, not a fundamental scientist. I think I'm just go apply it and go applications and get things moving forward.
And I guess with that group, you also have quite a lot of facilities now that enable you to really investigate, not just, I guess, from a modeling perspective, which in a way is a lot of your origin story, but you have the ability to collect data in the field, but also in your own laboratory treatment plant.
I've always liked the combination of experimental work and modeling. I would not be a good theoretical model. Even though my main work may look like it's theoretical modeling, I would not be able to do that a long time. I think I need this confrontation with reality and learning from reality to see what you can do. So I've always liked this. So my PhD was about this. My work in Ghent was about different things. And when I started in Modelo, the first thing we bought, because we got a little investment fund, the first thing we bought was measurement stations to be going out in the field and measure things, just water quality, basic water quality stuff. And then one of the big things we were able to do with the department as a whole, I think the department that we have is a nice department, is civil engineering. So it's civil structures, it's geotechnics, and it's water. We got along really well. So we wrote this big project and it's called Infrastructures for Sustainable Development of Cities. And that was a $20 million investment fund project. And $8 million of that was going to the water sector. And so quite a lot of money went into this pilot facility I'm having now, which is like for the rest of my life I can work with that. It's now 5 years old. And it's fully instrumented. I want to have continuous data collection. It is nice in terms of experimental facility because it has 2 parallel lanes. So you can always compare 2 things. You can run a treatment plant like this and the other one does something different. You can compare directly with the same wastewater. So that allows you to do quite interesting research.
So just for the listeners, so this is a miniaturized wastewater treatment plant, similar to the things you would see in your city.
Very standard. It's a very standard plant in terms of configuration. It treats the water of about 100 people. That's the size of it. So it's 10 cubic meters. It's not small. It's like a hall. So it's 10 cubic meters big, and it uses wastewater produced at the campus. So it's the students' wastewater that we treat.
Oh, practical.
With some kindergarten as well. So we have some young people producing, but it's very similar to municipal wastewater, what we had. And it's practical because it's local. So we have real wastewater. It's not like you don't have your pilot plant somewhere at the city treatment plant. You have to drive half an hour to get there. No, we just go down 1 floor and we're working at the plant.
And you're already there.
Yep.
I guess I'm calling it wastewater treatment plant, but as far as I understand, in the sanitation field and the urban drainage field, that actually has been changing.
That
in the
term
last
is
few
out.
years.
It's outdated. You should not call it wastewater treatment. I do still, but I'm stuck with the words that I used in the beginning of my career. Now it's different.
And so now it's different. It's called a water resource recovery facility.
Yes, and in French it's very nice. The French word that we came up with in Quebec is une STAR. And it's a Station de Récupération des Ressources de l'Eau. And it's very nice to call it a star, right? It's like everybody understands in star, everybody knows what it is, and it's more easy for people to remember than a WRRF or a WRF or something like this. So that's nice what you did in French with that term.
I think it's WRRF.
Yeah, WRRF or WRF. Some people say WRF.
WRF. I guess it's
like a dog.
Yeah, it's kind of funny, but in a way, it sticks in your head when you have these acronyms.
Yeah, you have to.
And so, what brought about that change? I'm sure you were involved a lot in some key publications around that, as well as some events.
I think the main drive was we do wastewater treatment, which is good for society, but people always see it as the waste part. So society looks at wastewater treatment as not something that is high value because it's about waste. So the people, it's like we want to get rid of it. But if you see what we've been doing since wastewater treatment started maybe 150 years ago, it's you recreate water, you reproduce water that can be put into the rivers and can support life again. So you recover that important resource, which is water. And people didn't realize even 50 years ago, then when water was released in the treatment plants of London, that it had gone to the persons 7 times. Because there's a cycle of water going to the city, which is reusing the water that was released from the wastewater treatment. And in many places it's like this. The water goes around. So it's good that the quality is good enough to be able to be recycled, even after, and you have, of course, have some treatment to be able to make it drinkable, but it's there. So water was there, but sometimes you heard about water reclamation facilities in America. You heard about this already, but then people start to realize, but there's much more in water. We have energy. We recover energy as biogas.
So it's not just about the water itself,
but
it's everything else.
So now the whole concept of water resource recovery facility is to recover the resources that are in water. And so one of them is energy. Pollution is organic, so you can make biogas of it, so it's energy. Then people started working on nitrogen recovery because nitrogen is a problem. So because nitrogen is toxic and leads to eutrophication in the rivers. But if you can take it out to protect the river, why do we take it out and make it again nitrogen gas that goes into the air and is lost? Why don't we try to recover it as a fertilizer? So then people found out that fertilizers can be made from the nitrogen, and phosphorus was recovered as well, because phosphorus is a very important element, because we run out, if we keep going like this, just mining, within 100 or 200 years, we run out of phosphorus, and it's an essential ingredient of your DNA, so no life without phosphorus. So we have to recover. So these things have come about. And so I would say like 7 years ago, the Americans said, we need to call it differently. We must make sure that people realize that what we do is something good. And so they came up with that word, water resource recovery facilities.
And then, STAR.
And STAR. Well, then we did the STAR thing, because in Europe, this word is not as popular yet.
Okay.
So we see that the publications in the scientific world, the publications from Europe still talk about wastewater treatment often, whereas every person publishing in North America will call it a water resource recovery facility. And people, of course, know, but it's not that completely entrenched into people's lives that this is a water resource recovery facility now.
So I guess we're in the middle of what is a real paradigm shift. Yeah. I guess Europe does have some realizations from what I'm reading in the literature around circularity.
Much more than North America. I would say, you're so far much further than what we are. And I'm frustrated being a European living there and seeing that they don't pick it up. No, in that sense, Europe is much more ahead. But in terms of the wastewater treatment, they have not picked up that promotion of the technology to say, look, this is circular economy, what we're doing.
And the terminology hasn't really caught on. And that's in a way one of your pet peeves, pet hates sometimes when you see that we confuse the terminology. I also experience this in my own field when I look into nature-based solutions, which seem to have been called many different names over the last few decades. And it seems that terminology evolves with the times, with the developments and also the disciplines. But what is your take on the terminologies? And we sort of talked about the mathematicians earlier because they like to be quite exact with their definitions. But it seems in other disciplines that seems to be a lot more, I guess, esoteric, a lot more flexible.
I think one of the first things I learned when I was doing respirometry with my colleague Henry Spanias was, he was a bit old, he had a bit more experience in terms of research. He said, when you write, never use a synonym. People get confused. So I still remember this very well, because when you write like your first papers, you try to show that you have vocabulary, you try to impress people, I think. So you wanted to use synonym. He said, that's not good. People get confused if you use two words for the same thing. People think you want to say something different. So I think in general, I think it's important to be very clear on what you say. And if you're in mathematics, you're forced to. Even though, if I look at my studies, my professor in mathematics that became my co-supervisor later on, he was confusing us all the time because every course he used different symbols for the same thing. He wanted to make sure that if you write a differential equation as dx dt, and the next day you write it as dy dz, mathematically that's the same thing. But as a student, you get confused because you're used to thinking dx dt is something. He played that on purpose, I think, to make people realize that it's about the structure of the equation. It's not about the symbols you use. But I think in general, it's very good to be very strict on terminology to make sure that people understand what you mean. Glossaries are important in a book. I wrote a book on dynamic modeling, and the glossary is one of the most important things. And I always fight for people that mix up validation with verification because these are different concepts. And I think it's important to do that properly, to make sure that people realize what they're saying has a meaning, and that word has this meaning, and that word has that meaning.
I guess validation and verification in particular, I've encountered that from you. So in a way, thank you for that little nugget of knowledge, because I also take very special care to use these words in their correct context nowadays.
Thank you for being a follower.
But I guess it makes total sense. This has also been drummed into me when I started my research career and also writing, that you want to communicate as consistent and simple as possible, because at the end of the day, it's not about impressing with words, but it's being consistent so that you can reach a broader audience if you can actually communicate more simply.
Even that may lead to a boring read, but we're not writing novels, right? We're writing scientific papers, I think. And if you want to write something different, then you can play around with all the vocabulary you have. But in this particular type of communication you do, you have to be, I think, very strict.
But I guess scientists tend to want to be poetic sometimes.
Well, yeah, but maybe not their best talent either.
Maybe it's not their best talent, yeah.
Some of us do, but I'm not.
But we digress. But in a way, Water Resource Recovery Facility, or WRF, or NSTAR, very fascinating paradigm shift that we're experiencing. And with that comes a whole range of challenges. And one, I guess in particular, is very attractive to you because you began your career in that, which is all about control. It seems, I guess if you take a step back in the history, a traditional, let's call it wastewater treatment plant now, really focused on emissions. The idea was the water going in should be of a much better quality before it enters the river or wherever it's discharged. And in a way, reading some of your work, there's a nice term for that. It's this one-sided specification. When you design a treatment plant, you need to meet that particular objective. But it seems that this is now changing, and control is also becoming even more important. Could you shed a bit of light on that?
So if you look at what we do in wastewater treatment, we try to reduce the impact on the environment. And we say in our standards, in our legal framework, we say if you discharge water, it should contain less than this type of pollution, or it should contain more than so much oxygen to basically discharge. So it's one-sided, which means that if you are into optimizing the process, you want to reach that with minimum cost, minimum resources. So least aeration policy, least chemicals, maybe smallest possible treatment facility, because that's capital, to reach that below objective. And if you go a bit too much below, it's not that bad, because the environment will be better protected, even though you have been spending too much money on doing it. It's not that bad. So if you look at control, what you do with control in that situation is you try to manipulate the process in such a way that you're just reaching the target, just staying below that line of 10 milligrams of nitrogen, for instance. So you minimize the resource to get there. And so the objective is one-sided. You just have to keep below. If your controller is not doing well, you might go a bit deeper and you have maybe spent too much chemicals to do it. However, if you go into resource recovery, then suddenly you come up with a product. You're not talking about protecting the environment. If you do a better job, you protect better, but it's not even if it's not objective.
Like the fertilizer that we were talking about.
Yeah, so the whole point is that you want to have a product coming out, the fertilizer, the organics that you want to sell. You want to sell something. Now, if you want to sell something like a fertilizer, you're in competition with the traditional chemical fertilizers that know exactly what they do, and they have big industrial facilities that make that, and they can give you a specification. Like they say, this per gram will contain so much nitrogen, plus or minus something. Plus or minus, so it means it's two-sided. So the challenge for the control people, for the process people in general, is now to come up with a way of running these WRFs such that they produce products that can compete with the alternatives, which means you have to be able to specify two-sided things. And that's much more difficult. You imagine you drive on a road and you can go right completely without any problem, and you just have to make sure you're not getting into the left rock. That's easier driving than you have to have rocks on both sides, right, to not hit. So that is, I think, as an interesting challenge that is asking more from the control engineers involved. And it's something that we see in general, that control engineers are getting much more involved in our systems because we need them more and more.
And so controlling a plant like this is really about, I guess, checking the concentrations, the volumes of water that come into the plant, adjusting certain levers and
valves and pumps
to make sure that the process itself then runs within this now two-sided range.
Yeah.
And I guess just to make things even more challenging for them, the raw materials, if we would call it that, it's not something you can have an inventory and you say, I need so and so much of this and these other ingredients. You actually you have to deal with the sewage that's coming from your city.
I said, I did quite some presentations about this WRF and the control paradigm shift for control people. So before you had if you look at wastewater treatment, then you had these legal frameworks that said, but if you really missed it and you messed up, the river was able to take quite a lot. So you were protecting the river when maybe you had some fish that would die, but nature is very resilient, so it recovers. So you had a forgiving environment which you didn't kill people, you may have killed some fish, so okay, we kill fish. It happens now and then, and society accepts that, so it's forgiving. You would not accept such a thing if you have drinking water production and you have people dying because you don't do a good job. And what I said as well is, in contrast to the chemical industry that basically mines really nice rock and knows what it gets and pushes in and even chooses what they're going to mine. They go to Morocco, they go to Chile to get their mines for phosphorus rock. They select the raw materials from which they start to produce this two-sided product. In a wastewater treatment, we just get what people dump at us. Yeah. So people just put in their toilets and in the industry discharge, the runoff from roads. People don't really look at this. There's no source control. We don't choose. We don't have a choice to choose this or that. At some point, we had a project that was called waste design, where you would work with industries and say to certain industries, we want you, we would pay you to have your wastewater because it's good for our treatment. And then these other ones, we would not like you to do your treatment yourself because we don't want your waste because it ruins our process. This was wastewater design, which was a kind of nice idea. It never made it happen, but it was a nice idea to work with that problem that you have, that we get the rainwater coming in, we get snow melt, we get runoff, we get whatever people dump into their toilets now. It's just giving big headaches in many places. And then if you have at the end a product to deliver that must be two-sided, tight to compete with things that come from a source selected industry, that's tough.
Yeah, when you need the concentration of your particular fertilizer or the nitrogen production process to literally not go beyond a certain upper or lower limit, then it's even more challenging. Yeah. And I guess the waste design experiment is a very interesting approach you could take, but it's not something you could sustain or roll out broadly because a city will grow independent of that.
No, it's all about how it's a service we provide to the city to make it safe in terms of pollution and the things that come with it. So you want to get rid of that wastewater and the waste. But you might think of not allowing people to throw whatever, what is it called, the wet wipes they throw into the wastewater, into the toilet, and then the pumps clog. So you can educate, I think, society to do certain things, or you can use financial means to stimulate certain behavior, to change certain behavior, such that the way we work with our waste is different and it allows you to recover easier. So it's also a value. This is what circular economy is about. You have to look at the whole thing, the whole chain, to make sure that every step of it makes a contribution to make that circle go well.
No, very true. And I guess that's also where more disciplines are now called to act upon this, to really understand, first of all, how the processes work, but then how we can influence from the outside before we even get to the plant, these raw materials. Mm-hmm. But I guess in the plant itself as well, there's a lot of different areas that you might have to then monitor and control and really be aware of. And this is a lot more stringent as well. One paper you wrote back in 1995 lists a lot of very interesting aspects of a plant that you could focus the control on to support performance, to support reliability, but also, in a way, the operation, to limit the failure issues within the plant or to control for the variability. Does a lot of that still hold true for this, or or is it becoming a lot more complicated now?
The paper you referred to was a conference paper. Sometimes I have these papers that I write for a conference that don't make it, and you say you should rewrite them and reuse them again. But it's available on the website, so people can download it.
We'll put this link in the show notes as well.
Ah, good, okay. Because I don't think it's that easy to find. But anyways, so this paper I wrote during my PhD. It was kind of my literature review and then rewritten for a conference where they asked me to talk about control and what you can realize with it in treatment facilities. And in that paper, I think I make a reference to the 1974 paper of a workshop in Clemson University. And I recently got a copy of the original workshop from Gustav Olsson, who is like one of the godfathers in our field of process control from Sweden. It's a blue, I never forget, it's a blue book, workshop proceedings, let's say. And what is what is the word? Maybe it's desperation you feel, or it's surprise you feel that nothing has really changed since 1974. That's 50 years ago, right? And next year it will be, in 2024, it will be 50 years that this Clemson workshop that many people in the treatment control area know about, because it was like the first time that people got together in the wastewater business and talked about control and what it could do. And what they, in that, I think, wonderful workshop, I was 10 years old at the time, so that wonderful workshop that they did was to set the scene for what was going to happen and why things were important in control, and that scene hasn't changed. So if you look at, I think anybody going into the control area of wastewater should read that chapter on the objectives or the usefulness of control, because it's still there. It's still as much motivating as it was then, is still applicable now.
1974, yes, definitely. It's a long time, and it seems that a lot of this knowledge has been established and is still very applicable today.
But I think it's maybe just intrinsic to the system that this is what it is. Why would things have to change every time? Some things are just stable, and we just have to repeat them now and then, that people realize, hey, that's what it's about.
I guess it's a famous quote: if it ain't broke, don't fix it, right?
Exactly, yeah.
Yeah, exactly. And so control, I guess we're controlling for the concentrations, we're controlling for many more aspects, and this also requires the collection of more data. I guess you would do this control in two possible ways, either in real time, where you're monitoring and you might have models predicting ahead, but also, I guess, in the planning for strategies over the long term, where you then use models more rigorously and you run different scenarios.
It's all about optimizing processes. So control, and automatic control, is something that can be at a millisecond. If you remember hard disks, but now it's not moving. Now it's solid state hard disks. But before, hard disks had a moving arm that were going on the different line. They were controlled at very high speed, because these things were spinning so quick as you had to, in I think it's million or microseconds even, that they were able to do control. In a treatment plant, things are a bit slower, luckily, so you have time. You can wait a minute, or for some things you can wait even a day to act upon what you've observed.
What's our general time step for a treatment plant? So how does
I would say a minute. I think the fastest things are on minute scale, the slowest things are on days scale. So you have some things you have to do automatically, because you cannot have an operator sitting there all the time to change things. Like oxygen aeration control is something that is fast. But on the other hand, you have like changing the composition of your biomass, so making sure that some organisms are present and some are gone away. So then you can work on days. You would not even see things change. You would take an action. It would take a few days before you see the effect of your action and see, is it going the right direction or not. So that is pretty special in biological processes in general, is that you have this whole scale of things from very fast, where you have to really be on top of things, to things that are just very slow. And like mutation is something that takes well, we haven't just gone to the virus, and we know mutations happening every so many months. There's a mutation coming in that's really making a difference. That's happening in a treatment plant as well. You have a mutation, or you have a different organism coming in that leads to different behavior, and I have to react because otherwise your treatment plant would suffer. So you have to have this attention span as an operator, things that you have to let automation do because you wouldn't be able to follow it. You would not be there at night to do it. And other things you can basically do every day, an evaluation of things, and then you would act upon it.
So it's almost like the treatment plan is sort of seen as its own ecosystem, its own environment.
It's life.
It's like it's its own little miniature world that you didn't have to, I guess, manage. Almost like a computer game, like SimCity, for example, which I used to play when I was a kid. Yeah. So that's fascinating. And so there's a lot of information, a lot of decisions have to be made as soon as possible because these systems can destabilize very quickly.
And what is very interesting is when I was starting in biomass, we were intrigued by the first simulators that came on the field. So the wastewater, you talked about SimCity, but we are talking about wastewater simulators that would help people to think about a process and would think about how can we run a process better. So they're using computer tools. And one of the things that we did in the early 90s was this software that is now called West, and it's one of the 4 softwares in the world that is used for simulation of wastewater treatment. The first prototype of that was built in 93, 94 or something. So this was a combination of people like me that were knowing models, and then people that were doing simulator development. So that was happening at Biomass at the time. They had people doing simulator development, but academic. So they were the bouncing ball thing. So they're very simple things. So they were thinking, well, we could do this. So we had this example from Canada, GPSX at the time. I said, that would be nice if we would be able to do something similar, but then better because we assumed that we were better in certain things. So we started developing that. And then the first thing they came up with had a version that ran. And it calculates very fast. And then us, the wastewater modelers, we got a user interface and they were very proud of the user interface. And we said, after a day of trying with it, we can't work with this. We were able to only make 2 graphs.
Ooh.
So what you do in a wastewater treatment simulator, you make a screen full of graphs because you have to look at all these different things I was talking about, things are going fast, things that are going slow. And you typically look at 6, 9 graphs at the same time. And as a process person, you would look at all these things and like absorb it and then work with it. And they didn't think about this. So the people that were doing the software never thought about that. People wouldn't like to have 9 graphs at the same time. And so they didn't look at the functionality for that, didn't write for it. So they had to really look at a good plotting toolbox to be able to make that happen. And it took them almost a year to get something that was then becoming useful for the process engineer that we were.
It's a very interesting parallel as well to the story you told about the mathematicians and other disciplines as well. And in a way, this is, I guess, becoming the issue now with the IT industry and all the other disciplines, especially in the development of models. You said the model is fast. I guess sometimes we have this trade-off between a very fast model and solving a lot of the equations within these models can take time if they're very detailed. So if it was a fast model, what about the accuracy of it? And does this change depending on what kind of process you're modeling?
I always say that a salesperson needs an answer within 10 minutes. So he wants to show to his client, look, you do this, and 10 minutes later, at least maximum 10 minutes later, he must have the result. If you're a PhD student, you're at the end of your PhD, you can wait a week. You just start a simulation and a week is fine. Early 2000s, Willy Guyer, which is a famous professor from EAWAG here in Zurich, now retired, but one of my example persons, he made a comparison of the complexity of models that people were using. And he compared from the mid-80s when the first models were being used, and they had activated sludge model number 1, which is kind of a standard model that is used for wastewater treatment by activated sludge.
It's one of the biological processes that take place in the plant.
The basics, where you look at nitrogen removal and phosphorus removal, etc. And then he made a variable, which was kind of the complexity, number of equations, number of variables, number of subsystems that you would look at. And he multiplied that and he got a number. And he plotted it as a function of time on logarithmic scale. It was perfect linear on logarithmic scale, so it means it's an exponential increase of complexity. And then he hit us in this presentation with another graph, which is Moore's law. And Moore's law is the number of transistors you have on a chip as they grow in time. And Moore's law said that the number of transistors on a chip goes up with an exponential of 1.8 per year. And the model complex that he got was 1.9 times per year. And you know what he said? What he concluded was, we are limited by compute capacity because we make models as complex as we can handle in our 1 week, or for the PhD student, or the 10 minutes for the salesperson. So they go up in parallel. So the compute power was limiting the use of model complexity. And we know that. We know that the things we do are just, at some point you say, I can't do any more complex because I don't have the time to do it. I will never finish my PhD. So that was an interesting development, that you look at complexity and model performance. And I don't think we give in on accuracy. We just tackle more complicated problems as we can. So we have a certain accuracy we want, and we will not tackle problems that are just too complex. Like now we're able to deal with the complexity of resource recovery, like getting a fertilizer out, how to model a fertilizer. 10 years ago, we were not able to do that. It was too long to calculate for the accuracy we wanted. 5 years ago, we suddenly had people doing it and doing it properly, being able to predict within a certain range. And typically in our field, it's if we're getting something plus or minus 10%, we're happy. So if you reach that accuracy, you're basically saying that's good enough. A chemical analyst would never accept that.
Okay.
They need 1%, 1 per mil or something as a accuracy.
Yeah, that's very accurate. I guess if the ecosystem in your plant survives and doesn't look weird, then I guess you're doing okay with your decision making around the model results.
Exactly. So the whole, it's what is it called? The proof of the cake is in the eating. So the proof of your model is it what you do with it? Is it making your plant work? And so what we see is that since 15 years, models are used for design. So the dynamic models that I'm talking about, they're used for design, and they are allowing to design to be good enough for practice to adopt these designs and build them and make them work.
I guess there's a certain trust we've built in these models now.
Yeah.
And with the computation powers now increasing quite rapidly, in, I guess, the sensors that we use to measure these systems and to help these model predictions becoming a lot cheaper as well. We're sort of entering this new paradigm. We keep talking of paradigm shifts today, but in a way, we're moving now towards this whole digitalization, Internet of Things kind of concept. And you sort of touched upon it in a keynote a few years ago for the water sector. But what were some of the key observations there? Are we really ready for digitalization? Is it happening? I hear paradigms and nicknames called Water 4.0 and some other words that have been used.
So if I look back at the whole experience I've had with AI, so just when I graduated in 87, there was the first boom of AI. I still think it was the first boom of AI in certain fields that people were talking about it. So I studied a whole year of AI methods and neural networks and was convinced that it's going to work. And we didn't. We didn't even start. It was just not possible. The tools were not ready. The data were not available. Around 2000, there was a next wave of AI attention. There was a new hype. So I was going with a student and said, should we try this? And he said, yeah, let's go for this. So we used, again, neural networks to do secondary clarifiers, a subsystem of the treatment plant. Let's try to model this with a neural network. We tried 6 months, a complete failure. So, and many people remember that time when AI was getting very much traction in certain domains, but in our field, we were not ready. What I realize now, the last 5 years, is digitalization and data mining and machine learning has become, again, in the attention because of the Googles and others that have made our lives so much different. And AI is in our lives everywhere. We tried again. And this time it works. So this time it works. And the reason it works, I think, is because we have gotten much more data. We have a lot more data. We are, I think, also more careful in collecting data than what we did before. It's become, we are getting more used to collect good data.
Careful in what way?
In setting up where to measure, when to measure, how frequent to measure, storing data, having metadata, getting information about your data that you store it better.
Okay, yeah.
So it's higher quality data and much more because the sensors have become cheap, so you can do more, you can put it on different places. But also the tools, I think the tools of AI and machine learning have become easier to find, easier to use. You have libraries, you have toolbox, you have Python now, which is just all over the place. So it makes it easier to try out things. Before you tried maybe one thing, it didn't work because you didn't pick up the right and you could only do two things. Whereas now we run a bunch of different algorithms and one of them works and then you're happy with it. So I think now the potential is there. We see much more demonstrations. And then the other part of the story is that in 87, AI was there, but people were afraid of it because it was artificial intelligence.
I guess there was a lot of reference to Terminator. Which
those type of things were happening then. Yeah,
Skynet.
Exactly. In the 2000s, I don't know what happened, why it didn't work, but I think now what you see is that AI is a hype, but it's a hype in the CEOs. It's the hype in the mayors of cities that want to have a digital twin of their city even. So you have this much higher adoption, also by society in general. Our phones are full of AI and we just accept that it's there. We're not afraid of it, we just use it.
How would we define a digital twin, by the way?
Oh, that's a difficult one. This is a terminology one where we have not converged yet. So digital twin for me is a system on a computer that mimics reality in real time. So this is where we have a big discussion. Some people say digital twins is something that describes reality in a very similar way. You can ask it questions and do some things. For me, a digital twin, because that's models. For me, that's models. We've done this maybe they're now a bit better, but we've done it for many years to make something that mimics. Digital twin for me is something that runs next to the reality and says something about reality. You can ask it questions, but it's at all point in time, it is mimicking that reality. So if something changes, digital twin will adopt it immediately as well because it's connected to that reality. And it also, when you do something with digital twin, it will connect what your decision is directly into the reality. So it's much more related to control and monitoring than before, making a model that helps you think about the system rather than to directly work with it automatically.
In relation to some of the other model-based predictive controls, is it something that you can then use to test scenarios, or is it something that's more data platform that you use?
I would say it can be anything. It can be an operator support. I think I'm using it for model-based predictive control because before it wasn't possible to do model predictive control. Now it's possible with these models have become part, and since they are running online, you can use it. This was the dream we had 20 years ago, but that was not possible. Now it's becoming, I think, increasingly possible. But I would say it's going way beyond. Digital twin goes about, I have a maintenance problem. Just look at how the system is now. I cannot stop my system now to work on it without disturbing anything else. So you can use your digital twin to talk about it. So it's helping in all aspects of operations of systems that you can basically check first with a digital twin before you go in and move into the real system. And sometimes it helps you to understand better what the system is about. You see, if you look at the reality, you might not see the details because there's water on top of it. So, but in your digital twin, you can dig in, you can dive into the water and see what's below it because it is describing what's happening below the water surface. So these are the interesting things about digital twins, that you can go into the details because you use all information available to you to reflect on what's happening and in real life. So that the real life aspect is for me an important part of the definition of a digital twin. It should be there that you look at it as it is now and not like what we think it was when we built it.
It's something that I guess we'll see how the definition comes about and refines itself in the coming years.
It's the discussion is not quick to converge. I know that first discussions were like the digital twin term. I know like 5 years now. And first I made a joke of it. And then I said, okay, I have to adopt it. I have to accept that this is the term we're going to use. But then I insisted on, and many people with me, luckily, have insisted on the fact that it should be connected to real life and real time, automatic, that you can really say something about that reality that you're trying to manipulate or optimize, whatever it is you want to do with it.
And I guess coming back to the whole digitalization and I guess the way we would improve our operation and maintenance of these kinds of resource recovery facilities, is it going to be more cost effective? Because in a way we're putting more sensors on, we're dealing with more data, we're going to have to process a lot more information.
It looks like it. It looks like that it's a beneficial thing. Of course, as we do this, we will learn when it is beneficial, when it's a good approach. It might be, I don't think you have to throw it to every problem. You don't have to throw a digital twin because in some cases it will not be useful. But as we go, we will learn when to use it. And I think the experience is going very quickly. Experience that we are building up is tremendous because so many people try out and are allowed to try out. The interesting thing about the digitalization is that the mayors and the CEOs want this. They have the money. And they want to have these ribbon-cutting events where they want to reap the benefits of what they've put money in. So that gives a lot of opportunities to people like me that can do this because we get all this chance and there's a diversity of applications that we see and we're getting the experience very much quicker. But if it goes wrong, and things may go wrong, and I hope there's no big disasters, you might have that everybody says, this is done. We don't go with this. This is dangerous. I think we've gone beyond this, but in the beginning when I talked about digital twins, I was afraid of that it would suddenly stop and that we have to make sure that the opportunity we get now from the CEOs and the mayors and other people in charge of money investing in this, We have to take advantage of this. So I said, don't waste time and study everything. Just run with the technology, try it out, demonstrate all these different things. And I said in a conference, this is hammer time, right? I'm a Formula One person. So when Hamilton goes for it, they say hammer time, go, 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 everything you can get, make sure you get it. That's what I said to people. We've done, as personal experience, I've done this 3 times, AI. 2 times was a complete failure, waste of time. I don't think now it's a waste of time, but we should not wait to try it out because it's now that we can get the funding to do these type of things. People are open to let us try things out.
You feel the time is right now, but I guess with any technological innovation, there's always that risk of backlash. But it seems like we have the means, the knowledge, the experience now to at least go forward with confidence.
So the early adoption is probably finished already in the drinking water area. In the wastewater area, I think we're still in the early adoption. It's more challenging in wastewater to work with sensors to get the collection done. The systems are a bit more complex, I think. So I'm convinced, but I'm seeing very good results and things are going forward and full-scale implementations are happening. So that's very promising.
I guess let's hope for the best in the future because I think it's going to be fascinating working with new sources of data as well that we're obtaining from it. I guess the risk is collecting too much data and getting drowned in all the data.
Yeah, the graveyards.
Yeah, that's a keyword I saw that I really liked when you wrote it in one of your publications. This data graveyard concept. You have to go in with a certain strategy with your data collection. You hinted on that. And some of the principles that I guess we gather from this is it needs to be relevant, it needs to be clear, reliable, and convincing.
So it's about, so I started with experimental design, making sure that we have a little amount of efforts, we can put a little amount of money, let's make the best of it and get good data. Experimental design never made it as a tool because we were able to quite easily get data and getting better. The problem now is that it's quite easy to get data. We just produce data, but then we don't do anything with the data. So the sensors are sitting there and they spit out numbers, but they're not stored in the proper way. They're not qualified in terms of how good they are or there's a problem, whether there's problems with it. So then that's what leading to data graveyards because you have data sitting there, nobody's going to use them. Because there's no information about it and their quality is not guaranteed and they're not even findable after a while because they're just sitting on hard disks and in the cloud somewhere without any way or tool to find them. So these are data graveyard, which is a pity because investment has been done to collect the data.
And I guess that increases the importance of metadata or the data of the data, documentation and cleaning the data and making sure.
If you look what I've done the last years, it's a lot about, so I'm much less about using data for control. For instance, I would love to do control, but I'm much more in the upstream parts of the data pipeline, making sure that your sensors are put at the right place. So still experimental design, making sure that they're doing the right thing, measuring the right thing, making sure that the quality is checked because people are sitting in front of Excel sheets looking at data and then eliminating data that are good. You need to automate this. If you have data pipelines that spit out numbers at tremendous rates, you must do automation of these tools that will kick out bad data and fill the data gaps that are created like this. Storing data it's very nice to use data once, but once data is collected, often it gives you history. You can look back at what happened before understanding. So historical data are often very useful, but they're only useful if there's metadata about them, that you know what the data talk about, how they were measured, where they were installed, what is the history of the sensor, who did that work. So these are metadata, and because only then those data become useful for a new use than the originally intended use. So these are the things in the data pipeline I think are essential to make sure that all the benefits that come afterwards of using data to make a model, to optimize a system, to make a control system, I've shifted my efforts in terms of research to make sure that this first part that is essential that people assume to be correct, it's not correct. These data don't come in nicely. They are dirty sensors. Their data are not coming with all the metadata you would need. You find out a year later or when your PhD student has left, you have a nice data set, but it's lost. The effort is lost because you forgot to write down things about it.
To assume the worst from the very start.
Yeah. Well, the worst not, but at least think about it. And with little effort now, you can make that these things remain valuable for a long time.
I guess you can relate it to a certain naivety in the fact that it's not just because you have the data doesn't mean that you can get further immediately.
Yeah. Well, you immediately see it when as long as the student is present, as long as the operator is present in a plant that has collected the data, they can still use them because his mind is the metadata. But as soon as that person is gone, then it drops and it becomes a graveyard. So it dies. The data die with the person leaving a data graveyard, which is a nice concept.
That's a scary thought, but really nice concept, and something that I think many people can relate to.
Mm-hmm.
It's been really fascinating. We've jumped across many different topic areas, and I think with that, you've also jumped across many different countries in the world as well, and we've really gone into, I guess, how things have evolved in different continents. You've sort of established your research life in many different countries that seem to be very close to you. There was Belgium, which you still work with a lot and you still visit because I guess you have family there.
Yes.
And you live with your wife in Quebec and you've got your group there. And you've been coming to Switzerland a lot, and this is why we've had the opportunity to sit down tonight. And I guess we're gonna have a lot more to talk about after this is done as well. And I guess there's also Sweden. There seems to be a big background story around Sweden. You've mentioned a person who I think has influenced you very strongly. Gustav Olsen.
There's some people make a big difference in your life, and I think in general, we should cherish them and thank them for what they've done to you, and you try to do the same with other people. I hope that somewhere there's a person that says, "Oh, Peter, that was an influence on me." So Gustav is very important. So Gustav I met in 91 the first time, I think, and he was a control engineer working in the nuclear system. So he was a nuclear engineer that combined nuclear engineering with wastewater engineering as two complex systems that he liked to work with and to apply his methods to of control and modeling.
So in a way you saw yourself in him.
I didn't know it in the beginning. It's just something afterwards that you realize, hey, there's a history that is somehow similar.
Serendipity in a way.
Yeah, exactly. And maybe it allows us to, or maybe it was something that was in our minds that made us connect that easily. I think Gustav is just a person that's very warm and supports young people in any means, and he did a good effort with me, I can tell you. But I see him do it with other people as well. So have been benefiting from the energy that he shares and the enthusiasm he shares. But he was very important because he supported me in the things I did from the beginning. Like in 1992, I organized my first conference. And I dared to ask Gustav to be the workshop chairman. Because he was open to this, right? I knew I could ask him because I knew he was going to say yes, probably. But I was a little hard asking him, and he said, yes, I will do that. And made that this workshop became attractive for people to come to, because they wouldn't come for me, they would come for Gustav Olsen.
There's a certain leverage there.
Yeah, oh yes, sure. Yeah. And he knew that, of course, that by doing that, he gave me an opportunity to shine, and that's why he did it, I'm sure. So this is and he's done many of those things. So just to give that example, as it allowed me to do this, and then got me into control and looked at more practice. He gave me the Book of Clemson. The 1974 book, I told he gave it to me. Look, you should read this. And I use it in my PhD. So these are people that are very influential on and I think it's good to realize that those people exist and that you can meet them and that you can benefit from them and that I should thank them and cherish the moments you've had with them, because he's now 80 years old, 82. And like my mother. So it's another generation, but it's what we do. You work with generations, and now I'm 58 and getting, young people are getting, like, are my children now already, and getting older children, even if you look at it. So that's what life in the science world allows us to do. I think it's very open, and especially in the environmental field, I think we're lucky that we are very open and sharing people in general, very motivated about the things we do, and sharing and making sure that we can make progress for society. That's, I think, what many of us are having in mind.
And it's the century-old tradition of passing knowledge down generations. And like I mentioned at the start of the show, you've been a very important mentor to me. And I guess in a way, what are some of that, those principles you can offer as advice to people wanting to take on this mentorship role, particularly myself, when I start supervising a lot more students?
I think the advice is that you see opportunities in people. And then you help them develop those opportunities. You see a talent, you say, okay, this is good. Pick it up and stimulate the person. I think everybody needs a pat on the back to move forward quicker. And if you don't have that, I think you can help people to understand themselves. You can be a mirror for people. With the experience that I have now, I see things in people and I say, oh, this is something that is good for you. And if you just explain it to the people, they get better in doing things. They get more enthusiastic in what they do. They know, if you know your strengths, you can exploit them. If you don't know, you might use a bad talent you have or a negative thing, you would waste energy on it. So I think it's good that people help you. We all need feedback, I think. And like I'm now a professor at university and we don't get any feedback. The feedback we get is from a colleague now and then, but often it's what I do. And when I'm meeting at an international conference, we talk about our lives and just you learn things about yourself through that, because within the university, there's no support, I feel. We're all in our little offices. We have a little company because every lab is a little company that's doing, but we're the CEO. We don't have a board helping us. We're too small as a company to have a board that gives you advice. So you're just sitting on your own and you do the best you can. With your collaborators, I use postdocs as a source of information to give feedback to me.
Oh, yeah.
And I think they like that, to be part of the organization and that they're allowed to give feedback to me. And I change my ways of doing, but it's a lot about talking to the colleagues and how they run things. So that's what I often do when I'm having a dinner with colleagues of mine in the same situation as I do, how they do things and learn in this way, how to do better.
And that's really beautiful to see that two-way dialogue, and that you always welcome that dialogue as well, because I think through that you also see your own weaknesses, or maybe you see similarities, and you start to reflect on it, I guess, on your own as well.
Oh, yeah. And it's the only way to make progress, I think. If you don't reflect on yourself, you keep doing the same thing, I think you're not very good in what you're doing.
We've seen the example in Gustav Olsen as a really strong mentor to you, and you've also mentioned a few others during the course of this episode. I guess, are there any other things you can think about, whether it's books, papers, seminars, or other people that have really changed the course or given you that inspiration to do what you do?
I think things that have changed my perspective on what I'm doing have to do with visits I had. I was lucky to have projects in Ecuador. I had a project with South Africa. And even though I didn't really work with them further, they made me realize that pesticides are critical, that working for low resource settings, making sure that sanitation is there, that was so confrontational. I came back from these visits completely disturbed, I would say, not knowing that this is real life. Okay, you see some things on television, but living it yourself and having somebody show you locally, that is so devastating, I would say. The word was I was devastated coming back from South Africa, for instance. I was completely appalled. I never ate a banana since I came back from Ecuador.
Oh, wow.
Because the pesticides they throw up. No, I will just explain that thing. So to have bananas here, you need to spread every 2 weeks pesticides to make that the bananas grow every 2 weeks. And the thing they do at that time when I was visiting there, so they have these planes going over the banana plantations, and they don't use at that time they didn't use GPS. They had it, but they didn't want it. It was too expensive, so they just put people in the plantations with a flag up. This is the start, this is the end. And those people were there, should have been protected with gear. Yeah. But it was too warm, so they didn't do it. And they were not informed that what was spread on them was dangerous. So that was one thing. The other thing I learned from there was that they have these planes coming over, and then they stop. There's a little river going in the plantation. They keep spreading. And then downstream people were just seeing these patches of oily substance, which is the pesticide and oily stuff because it has to stick on plants passing by. And people take out the water for cooking with pesticides at high concentrations in them.
Even though it was clearly visible in the water.
Yeah, and they were not informed. Imagine, you should not do this, first of all, to throw this, but you should inform the people, look, there's going to be something passing by which is not good for you. So I never ate a banana since then. And so these are things that is in my field. So I look at pesticides and how they are, model pesticides, how they behave in the environment. But this was very confrontational in the fact that you see that us, society, we don't want to pay for our food, not as much as its value is. We want to have it as cheap as possible. And then you get plantation people that do the things they can to make it cheap, but not considering the local people and the impact they have on the environment there. And that's this with many things I have this type of thinking of. But I lived it and I saw it and I said, well, that's not acceptable.
And it makes you really reflect and try to improve.
And then, so then to bring it in my own work, I have the part of pesticides you have to be very careful with them. You can use them, but you have to be careful with them. You have to know what damage they do and how long they will last, etc. And And then certain pesticides are not allowed, other ones you can live with. So the whole pesticides is a big thing in my career, even though pesticides have been gone out a bit because I don't do river basin management anymore. I don't look at agriculture. I look at the urban system, but even there pesticides are around because we use it in our gardens and stuff. So,
and who knows, they may become an issue in the future with this whole push for urban agriculture as well.
Sure, no.
But it is fascinating to see what travel can really do to open up one's eyes about the world, and I guess how that then trickles back into your work.
And travel is especially important if you have a local host that shows you things, because you can travel and do the typical sites, right? You can do tourism, then you don't see these things. So it's the people that are in our field that point out things and that are relevant to our work that make an impact on your work as well.
I totally agree. And when I travel myself, I tend to want to see the city for what it is and not just the sites. Yeah, you go to them, but you kind of want to really get a feeling of what it is like to live there. And
you have to work a bit when you're on traveling. You have to work a bit and being inspired by the things that are happening there to bring it back home to your work.
I guess it's the appeal of being an academic. You get to go to conferences around the world and to be able to then couple it with some form of sightseeing or some form of cultural experience.
But I think it's also about being interested in the local situation so you can go to a conference just as a tourist as well.
That's
then
true.
You don't benefit from that. I think you should take advantage of the fact that you're meeting their people locally and you can talk to them and talk about their problems, the water problems in our case, and then learn about it and bring that back with you to help you change course in your research and make sure, like I now try to have, since I went to South Africa, I try to have somebody in low resource settings work on latrines. I'm modeling latrines. Okay. Which is not like my core business because I'm a technology person, but that made me say I should do something. I look at consumer adoption of toilets, dry toilets, because I know it's useful in other places where, even though I'm normally on a sewer system, just that helped me to make sure that I was investing my time in something more than just the things that I'm normally used in our own environment, just to make sure that I can contribute as well to other things with the skills I have.
And it reminds me of one of my own personal experiences as well when I visited New Zealand just after the earthquake in Christchurch and felt I want to see how I could help in one day, or at least to shed some light on how we can, I guess, improve the city's resilience to disasters as well. No, fascinating. But I guess traveling as well as an academic, takes time. And in a way, with academia and being a professor, running a group, time management is very challenging. And so what tips and strategies can you offer in terms of time management? How do you maintain a balance between, I guess, your professional and personal time? Because you spend a lot of time, or at least I've seen you and your wife are here in Switzerland. You've been here for a few months, and it seems like you always have an opportunity to go somewhere, to see a city, or to just walk along the lake. I've bumped into you in Zurich itself.
I would say that my time management is a bit different than many people, I think, because my work is my hobby. People would say, why don't you take a book? And I will take a paper. Because I prefer to read a paper than to have a book. I read hardly any books anymore. I watch my Formula 1 races. I look at football sometimes. I like to have a walk outside. I like nature, to be outside. But I like my work. I really like my work. And people say you're a workaholic. Sure, I'm a workaholic, but I'm a hobbyholic. I like the work that I'm doing. I'm inspired by the work. It's intriguing me. I often people would not understand why I take something from work. It's just because I like it. So that's particularly in my time management. That is a lot of time I want to work. I think I've become very efficient in terms of working with people, correcting things. I'm a very fast corrector. I can read and correct very quickly. So I've become efficient, I think, much more than like 20 years ago when I was in Belgium. I was going for a burnout, as I said before, because I was having too much people. But now I could run the same number of people. I think I would be able to run at the same level, but because I've just become more efficient in doing things. It's about when do you mails and when you try to minimize disturbances and focus and find a good balance. I think I'm still in a very good shape. So I have many hours a day that I can devote to many things. And I've also become a bit less deadline driven or delivering driven. So if I don't make it, I don't make it. I make people accept that I didn't make it. And I'm sorry for this, but I will just explain them. Sorry, didn't make it. It was too much. And I feel a bit sad about it. But on the other hand, you have to also make sure that your life remains feasible. If you're just overdoing it, you're not going to end well. One thing I learned during my career was it's okay to not deliver. It's okay. As long as you do your best, it should be enough for the other people to accept this is what you do. And that made that the pressure is different because you can become very inefficient if you're like living under too much stress or pressure. And I have another thing that I have is I can work at warp speed.
Okay.
I can do a 2-day rush job that is very efficient. So I learned myself that I can do this with a hard deadline, like a really hard that I know I can't miss it. I can squeeze my brain to deliver at a very high rate. And I call it, I'm going warp mode now. So I'm going warp mode, but then I cannot do 2 days afterwards. I'm not doing anything. I'm just exhausted. So I then have to completely stop doing anything because it's just been exhausting. But I can do that for 2 days, let's say. I can and deliver really a lot in 2 days.
But that is essentially the balance that you would then strike in a way.
Yeah.
You go at warp speed or warp mode, as you said. And I've heard you mention that to me on a few occasions as well. And then I guess after that, taking that rest, that well-deserved rest. I suppose it makes total sense because if you make something your hobby and then you start to burn yourself out, then you kind of have nothing left, right?
Sure.
So there's a certain risk to that.
Hobby should be fun.
A hobby should be fun. No, I totally agree. But in relation to that, what was one of the most challenging situations that you've ever faced in your hobby or career to date, and how did you overcome it?
The hardest moment, I think, the most difficult moment, like no sleep and stuff, was when my first professor got mentally sick.
Mm-hmm.
I had this was early in my career, so I had done my master thesis with him, and he was become professor in Leuven, the other university. It worked fine. It was a wonderful opportunity because I was the first teaching assistant. I saw my academic career was like, and he was really good. Peter Raakit, for instance, here from Jalwak knows him as one of the developers of really modeling methodologies. And if I see what I do now, it's still what he trained me in those 3 years I was able to work with him. So I started my first PhD study with him. And it was nice. It was about fermentation and antibiotic production and modeling of that. But after 2 years, he was sick. He was mentally sick. So he got schizophrenic paranoia.
Oh, no.
And that was really hard because first of all, you don't know what's happening. It was gradually going down. And it's very scary to work with a person that has that because you don't know how to handle it. He's in trouble. Obviously, he was in trouble. And that was affecting our lives at the lab. And so then you'd have this sleepless nights because you on one hand, you know he's not good. So how you want to support him because good and bad moments. On the other hand, you have to be for yourself. You have to basically protect yourself. And it took a few months before we dared to go out above him to say, look, there's a problem. This is unbearable for us to be here. We were 3 PhD students, and all 3 became professors, by the way. And top-notch professors. So they were really well trained by him. But then the university understood that this was a problem. So they gave us the okay to look for another job because we had a task. We were obliged in theory to stay on because we were teaching assistants. They gave us a chance to go out. And then this was then the most important moment in my life, I think, if you look at it. I was trying to get out. I was looking for a job. I have seen a job offer in a company that I worked with that were selling sensors and equipment. I was going to become a salesperson.
Oh.
So that would have been a different career, I think. But they wanted when you applied, you had to provide a reference person. So I was thinking, who's going to be my reference person? And then I thought about my professor in environment engineering, Willy Verstraeten from Ghent University. I think he liked me, so he will probably say something good about me. So I called him. This was still the time, no mails, it was calling. So I called him, Professor Verstraeten, would you be willing to be a reference? And he was so quick. This guy was so quick. He saw the opportunity. He knew me, right? He knew what I was doing a bit. We had seen each other a few times in the course of those 3 years. And he said, are you looking for a job? I said, yeah, I'm looking for a job. Well, can you come to me? Because I was living in Ghent. I was traveling to Leuven 1 hour by train every day. I was living still in Ghent. This was on a Friday evening. So he said, would you be willing to come to my office? Because he was always working on Saturday morning in the office. Could you come to the office? He made me an offer.
Wow.
To become a PhD student with him on modeling because he saw the opportunity of modeling. He was not a modeler himself, but he saw an opportunity that modeling was something important. He saw that opportunity with me and he gave me a chance. And that little phone call, after a very hard, difficult time, that phone call made that my life changed into what it is now. Because then he became my mentor. He supported me in that. He let me apply what I learned from the first professor in the environmental world. And that made it happen. And then with people like Gustav Olsen, etc., then things moved on.
In really challenging times, you sometimes really see that an olive branch appears out of nowhere when you least expect it.
Yeah. Nice picture I have now. Thank you.
It's a fascinating story, and thanks for sharing that. It's really amazing.
Oh, it's one of the stories I tell a lot because it was so it was such an important, and people should realize that it's important to remember when things are really changing your life. Like the other thing was the whole thing about Montreal. If we had not lived in Montreal, we would never have lived now in Canada. That made a complete change. I don't know what I was going to be doing in Ghent still. I don't know. I might have had the burnout, right? So this is the things that happened if you take those opportunities. And serendipity is a keyword that Willy Verstraeten also told me, like, there's something passing by, but always be open to seize it, right? This is serendipity. Just be open-minded to things that pass by, just to grab it.
Yeah, the doors will open, I guess, automatically.
Yeah.
What other advice can you offer to, I guess, young engineers, young bioengineers and environmental technology engineers starting out, or just generally young academics?
I would say that if you're an environmental engineer, call yourself lucky. And any person around will be willing to help, because the water and environment are motivating people. So if you meet other people that are in the field, they are very motivated to make progress. They work for society. They have a motivation for society. I think there's very few environmental engineers that are selfish and don't look at themselves. They want to do something for society. So make sure that you realize that, and that you basically can talk to anybody to become a person along the way. As a young professional, I think you go alone is very, very boring. And this is a field where you can really go together with many people and share and do things and use your talents and combine it with other people's talents. So young people should realize that this is important, that you can, not everybody, you will not get along with everybody. There's so many people that want to work with you. I think that's a very nice thing to say to young people, that this is the way our field works.
I guess there's a famous quote from a poem of a panda. I'm going to butcher this completely, but it just came to mind, and I remember it was like, it's not the destination, but it's also not the journey either. It's the company that matters in the end.
There's another one about moving. If you want to walk fast, go alone. If you want to get far, walk together.
I like that. We'll have to definitely find the attribution for that. Put that in the show notes as well.
Mm-hmm.
But Peter, thank you very much for this talk. It's been incredible to hear your story, to talk about all these different aspects. And we've only scratched the surface of what you've accomplished in all the work you've done. And I look forward to doing this again in the future, because I think there's a lot more that we can really go deep into. For example, uncertainty is obviously one aspect, and we're always uncertain in the world, but that's, I think, something that can take up a whole episode on its own as well. And thank you to you listeners as well for your time and company on this very insightful journey. I think it's been really fascinating and filled with a lot of advice for young academics, young engineers who want to go together with others, or to go along with their peers in this journey. And that our world is really becoming this super interesting place where data in a way matters, and how this is going to act out in the next decades is going to be very fascinating to see. So we'll definitely have more information about this in the show notes, but where can people reach you if they want to get in touch?
Well, there's only one person in the world that has my name, I think, that is you can find on the internet. So it's Peter Vanrolleghem. If you find that name, that you can probably find information about me. Modelo is also something that is quite unique in the terms. You just have to remember that Modelo, it sounds like model with an O, but it's model EAU. And the name of our team was called Modelo because it's modeling water. And the French word for water is O, EAU. So that's also quite, I think, very easy to find. If you just type in Modelo, you'll find us.
No, that's great. And we'll put that link as well in the show notes. But otherwise, Peter, famous last words. I'll leave the one message to you for listeners to take away from today.
I will repeat what I said before. If you want to go fast, go alone. If you want to go far, go together. I think that's a very good idea for people that are in our field.
Thank you very much. And thank you to you listeners for tuning in to this incredible conversation with Professor Peter Vanrolleghem. As mentioned, you can find links to references and articles all in their digital and microscopic detail in our show notes over at petermbach.com/podcast. If you enjoyed this show and are looking forward to more episodes, please do subscribe or follow this podcast on Spotify, Apple Music, or wherever you are listening from to be notified of the latest release as soon as it becomes available. I would be incredibly grateful for this, as it helps me to reach a broader audience and, who knows, perhaps inspire better care and metadata documentation, or just a much greater appreciation for the many mentors in our lives. If you'd like to know more about me or my work in general, you can also check out my website at petermbach.com, my YouTube channel, Peter Marcus Bach, that's Marcus with a C, or follow me on Twitter at Peter M. Bach or Instagram at Peter M. Bach 87.
If you have feedback or suggestions, or just know someone who has an inspiring story to offer, please feel free to reach out to me on social media. The podcast's intro and outro song is called Bicolia by Bureaucratic. Stay tuned for our next episode and next guest to hear how they are tackling the grand challenges.